Hello everyone! Welcome to the second part of this course. So we had review week last week, and this second part will be focusing on the Sturm-Liouville theorem. We'll first do some work on the Cauchy Euler equation, Frobenius method, and numerical methods to solve ODEs. So this week will be an in-between what we covered in the previous part of the course and the build-up for the Sturm-Liouville problem. In this video specifically, we'll be looking at the Cauchy Euler equation. It's another of the many special equations that can have specific solutions, but this one will be applied in a bunch of other situations. In particular, is a special case for the Frobenius method itself. So let's delve into it. This is the shape of the Cauchy Euler equation. It's a general shape. It can be order n. We're assuming y being a function from 0 to 1 to r. And as you see, it's a linear non-constant coefficient ODEs, and the coefficients are always a constant term times x at the power of the derivative. So we have the term x at the power n times y at the nth derivative, then a constant times x at the power n minus 1 times the nth minus 1 derivative of y, and so forth. For example, we can look at x squared y second plus c1x y prime plus c2y equals to 0. As a first guess, we can think of y as a monomial in x, so x has some power r. Because if x has the power r, then the first derivative of y times x is again something that is x at the power r, and the second derivative of y times x squared is again something like x at the power r. So it seems like a reasonable assumption. Let's see how this works out. So we just plug all the information we had previously. So we plug our assumption on the shape of y in our derivative. We have a couple of terms popping up. And we take x at the power r away, and then we have just an algebraic equation that should be equal to 0. So a sufficient condition to solve the Cauchy Euler equation is that our algebraic equation equal to 0 has a solution. But this is a second order algebraic equation. We should be able to solve it automatically. So let's look at the possible cases when solving this. So the first case is there are two distinct roots, lambda 1 and lambda 2. They might be complex, but we know how to do complex powers, so our y general solution is equal to a linearly independent sum of x at the power lambda 1 and x at the power lambda 2. What happens when they're the same? You remember that when we're supposed to have two solutions and we end up having only one, our approach is usually to do variation of parameters. So we are assuming that our equation in R is equal to 0 and has a determinant equal to 0. So we can actually solve explicitly for lambda 1 and lambda 2 as both being equal to c minus c1 minus 1 divided by 2. So our first solution is the same as before, a constant times x at the power lambda. But for the second solution, we want to assume, with the idea of the variation of parameters, that a is actually a function of x. So what would a as function of x satisfy? Well, we first notice that y2 is equal to a as a function of x times x at the power lambda, where x at the power lambda is our initial solution. So y2 is a product between a function we don't yet know and the function that is the first solution. We can do the various derivatives, first and second derivatives of y2. We remember the Cauchy Euler equation that we're trying to solve, x squared y second plus c1x y prime plus c2y equals to 0, and we plug all these terms in our full equation. And now we remember that y1 is a solution, so we can actually cancel some terms because they're exactly the Cauchy Euler equation times a. And that doesn't matter, they still sum up to 0. So here we are with a simplified equation in which we remember the shape of y1. So we replace y1 with x to the power lambda. And now we retrieve an ODE. This time the unknown is capital A that we're trying to solve. We simplify by x to the power lambda plus 1 because we have that term everywhere. And we remember that we have computed lambda explicitly, so lambda is minus c1 minus 1 divided by 2. So this coefficient in front of a prime is actually equal to 1. So we retrieve an equation for a that is very simple, an equation we can solve by hand. So x times second derivative of a plus first derivative of a equal to 0. We can change the variables from a prime, we call it u. Now it's a first order ODE in u, we know how to solve it. If we have u, then we can integrate to find a. So u is k1 over x, with k1 any possible constant. Then a prime is k1 over x, we integrate this, and we have k1 log x plus k2. With k1 and k2 constants, it's a second order ODE, so it makes sense to have two constants at the end of the game. Now that we have a, we can plug it in our definition of y, and we retrieve the full solution for repeated roots of the Cauchy Euler equation being the product of x to the power lambda times logarithm of x plus a constant.